Okay, so this is still section 12.1 to 12.2. We're on our 5th page of examples for this very first section in dynamics, looking at kinematics. Remember kinematics, the things that move, we don't really care about where the force came from, we're just looking at motion. So if a ball is thrown upwards from a height of 15 feet with a velocity of 10 feet per second, how much time passes before the ball hits the ground? So this is something to always keep in mind. When I say draw a free body diagram, they may look a little bit different than in statics. So here I am, I'm standing on a giant box so that I am throwing a ball from 15 feet up, okay? And I'm going to be throwing that ball with an initial velocity of 10 feet per second. And I want to know how much time before the ball hits the ground. Well, the ball's going to go up, and what's going to happen to the velocity as the ball goes up? That velocity, because of, guess what? We have acceleration acting in this direction. If it's feet per second, it's 32.2 feet per second. So I try not to call acceleration negative. I just draw it in the opposing direction. So we are throwing the ball up. Up here, I know that the velocity is going to be 0. Once it hits 0, it's going to be coming all the way back down. So how much time passes? I'm going to need time for it to go up, and I'm going to need time for it to go down. Because we're starting at 15 feet up, the time up will be shorter than the time down. As we come down and hit this magical point right here with 15 feet left, it will be coming down at 10 feet per second. So we could look at it as time up and time down to this point is the same, and now we're at 10 feet per second coming down. What does the time it takes there? So there's lots of ways to approach these problems, but I think drawing a picture is best. So let's throw the ball up. So I'm going to call up as my positive. We have V equals V naught plus AT. S equals S naught plus V naught T plus 1/2 AT squared. V squared equals V naught squared plus 2A S minus S naught. Okay, so the ball is going up. I know the initial velocity. I know the final velocity. I know my acceleration. I can quickly determine the time that's going up. So I'm calling up as positive. That's how I know whether to call it a positive or negative. So if I'm looking at this, V equals V naught plus AT, my final velocity is 0 because gravity slows it down. It changes direction. My initial velocity is 10 feet per second, plus my gravity is working down, so it's a negative 32.2 feet per second squared times time. So as I pull this over, I get negative 10 equals negative 32.2 t. So 10 over 32.2 equals time. So I can quickly find that my time equals 0.31 seconds. So that would be from this point up to here. And that's where we have lots of different ways to do this. I know that if this is 0.31, then this is also 0.31. And I could approach this as I know the velocity at this point is 10 going down, because what goes up must come down, same amount of time, same path traveled, and I could calculate the time it takes to go from there to there. Okay, so that would be one approach. Or I could figure out how far it is to the top and then look at the entire distance coming back down. So let's figure that out. If I'm going up, then I have S equals S naught plus V naught T plus 1/2 AT squared. I don't know how far up is, but I'm already starting at 15 feet. Plus 10 times, it takes 0.31 seconds to get there, plus 1/2 times negative 32.2. And then again, I have that t squared, 0.31 squared. And if I look at this, my positional change is to 16.56 feet. So I know up here, this whole distance is 16.56, okay? So now we're gonna have the ball falls. And again, I'm looking for time. I know that my initial velocity at the top is 0. I know that my positional change is going to be 16.56. I know that my acceleration is 32.2. going down. So I could start at the top and I could say that my initial is 0, my final is 16.56, and we're going to call down as positive. So this is 0. This is 16.56. My acceleration is working in this direction. My velocity works in this direction. So let's just call down positive. And if I do that, I know that I have I don't know the final velocity when it hits the ground, but it better be bigger than 10. I do know my positional change, so I could use this to calculate the time that it takes for me to move. So we have S equals S naught plus V naught T plus 1/2 AT squared. And if this is 0, my final position is 16.56. It's positive because I'm calling down as positive, equals 0 plus my initial velocity at the top is 0. It had to change around, plus 1/2, 32.2. 32.2. And again, this is positive because I'm calling down positive, time squared. And if I do that calculation, I get that my time is 1.01 seconds. So that's the time down. This is the time up. How am I going to find that total time? So my delta time is 0.31 seconds plus 1.01 seconds. So my delta t equals 1.32 seconds. Okay, and again, go back and play around with this, calculating if this is 0.31, what is the time that it takes to get there. And so yeah, it's just a great way to play around and learn how to do. Okay, so this problem is probably a little bit more difficult than what we've been doing, but hopefully you're kind of picking this up. We have car B that's traveling a distance D ahead of car A. Both cars are traveling at 60 feet per second when driver B suddenly applies the brakes. We don't want to hit this person in the crosswalk, causing his car to decelerate at 12 feet per second. It takes the driver of car A 0.75 seconds to react. So slams his brake, 0.75 seconds, slams the brake. That's before their deceleration hits. When he applies the brakes, he decelerates at 15 feet per second. Okay, determine the minimum distance D between the cars so as to avoid collision. So we're going to have to think about kind of what's going on. These two cars are traveling. Car B slams the brakes. So I'm going to move this person out of the way, and I'm going to put car B over here just so we have a little bit more space. So here's car B, and car A is going to be like right up on his bumper. We're going to make him look a little bit different. Okay, so I'm actually going to have information for car B and then information for car A because they're both independent on the same road. So when they get to this point, we need to make sure that the acceleration of car A is equaling the acceleration of car B so that we don't hit, okay? And at this point, if I look at my initial position of him driving, initial position driving, they are now at the same final position S because they're bumper to bumper, okay? So I know that my positional change of A has to be, we are at the same position. So if B moves this amount, A is also moving that amount plus this distance D, okay? So they'll both move, but A has to also move up distance D. So what we're going to do is we're going to call this like ground zero. This is S initial. Okay, S initial. And I know that car A has an initial velocity of 60 feet per second. And I know that his acceleration is negative 15 feet per second, but that is after 0.75 seconds. Okay. Car B, our car velocity is 60. Our acceleration is 12. And we immediately start at time equals 0. Okay, so this is where we're going to get the picture started. I know that VA has to equal VB, SA is going to equal SB. So let's just get started with with car A information, and I mean car B information. So car B, constant acceleration. So we can use our constant acceleration equations. V equals V naught plus AT, S equals S naught plus V naught T plus 1/2 AT squared. V squared equals V naught squared plus 2AS minus S. Well, we don't know the positional change. We do know something about time, so we're going to start with our time equations because we know there's a 0.7 second lag. So car B, our velocity of car B at this point is the initial plus A times T. So our initial velocity is 60 feet per second plus our acceleration is negative 12 feet per second squared times time. Okay, I don't know the time that it's going to take, but this is what we have. So my velocity of B equals 60 minus 12t. Okay, now I can do the same thing for car A. I can say the velocity of A is also the velocity initial plus A times t. So my initial velocity is 60 feet per second plus, I'm slowing down at negative 15, but I have to keep in mind, is it the same amount of time that we're slowing down or is there a lag? So here is where I have to remember to say, t minus 0.75 seconds. It's slowing down a little bit slower, but it's got a faster rate. So if I know that my velocities have to be the same in order for A just to be riding on the bumper of B, I can now set these equal to each other. So I have 60 minus 12t equals 60 plus negative 15 times t minus 0.75 seconds. And I can work all of this out. I'm going to just go ahead and remove that. And I have negative 12t minus 15 equals negative 15 times t minus 0.75. And if I calculate this out, I get 3.75 seconds. So that's how long it's going to take. Slam on the brake, move to this position so that we don't hit Guy in crosswalk. I guess that's like a Godzilla, okay? Little bit slower time, faster acceleration rate. So let's do the same thing and let's look at that positional change because we're trying to come back and get this distance, okay? I don't know where to start. I'm just going to start with what I can do, draw a picture and come up with some relationships. So let's look at car B again. S equals S naught plus V naught T plus 1/2 AT squared. So I know that car B, okay, its initial position is not at S0. Its initial position is D ahead. D plus its initial velocity is 12. The time is 3.75 plus 1/2 acceleration of negative 12, 3.75 squared. So here is my equation for the positional change of car B in that 3.75 seconds. And remember, it's starting a distance d ahead of our starting line. So let's do the same thing with car A. So car A, we have to think about this a little bit different. So we can still use this equation, but what I want you to think about is for part of this, we don't have any deceleration. For the first 0.75 seconds, we don't have deceleration. We have that lag. So we're going to kind of have to look at this in two pieces. So car A. So we're going to look at, okay, we're starting at 0 plus 60 times, okay, what is the amount of time that we're going at 60 without acceleration? That's going to be 0.75 seconds, okay, plus 1/2. Well, at first we're not decelerating. Now we've hit the brake and we are going to be moving a little bit farther down the road, okay, a little bit farther down the road, and I've already taken care of that I started at 0, and the amount of change that I'm going to have during this second bit of time is my velocity is 12. The time is going to be 3.75 minus 0.75 plus 1/2 negative 15. And again, it's 3.75 minus 0.75. So we are going to be traveling for 0.75 seconds without acceleration. Then we are going to be traveling for 3 seconds while we're slowing down. Okay, SB equals SA. So I'm going to get D plus 12 times 3.75 minus 6 times 3.75 squared equals, so our only unknown here is distance, equals this giant mess. 60 times 0.75 plus 0 plus 12 times 3 minus 7.5 times 3 squared. So I hope that's making sense to you, how we're having to set this up as a two-parter. And the only unknown I have here is D. And if I calculate this out correctly, I've got 16.875 meters. So this is happening pretty quickly. And I hope that helps. I just always draw a picture, always set up what it is that has to be happening at this point as we've traveled down. They're bumper to bumper. Their velocities have to be the same. For the shortest distance. Now, if this guy slammed on his brakes and we had a bunch of meters in between, that's a different story, but it says just to determine or just to avoid a collision. So if we're just avoiding collision, we are right here together.